So for week 6, we're going to tackle the chapter of capacitor and inductor. So we'll start with the first part of the video on capacitor, and then we'll go into the topic of inductor. So let's begin with capacitor. So what's make a capacitor? Basically, capacitor is made of two basic components. The two components are basically the first one is conductive plates, right? Two conductive plates, and in between the conductive plates we will have the second part, which is the what we call a dielectric. So what is a dielectric? So the component here in the middle. So a dielectric is basically a component that doesn't conduct electricity, right? So it is a component that separates between the two conductive plates, which will later I'll explain how it works. So basically, when we look at the capacitor that you have in the market or you're using in the lab, they look cylindrical. Most of them are cylindrical, except for some of them. For example, here we'll see something that looks like a squarish plate, but others are these are plates, but others are usually cylindrical. So what happened? What's the difference with what I've explained here? What I've explained is basically two conductive plates, but now it's not a plate, it's a cylinder. So basically it's a sheet of conductive plates that are rolled into a cylindrical form, right? So that's what we have inside here. So how does a capacitor, what's the basic principle of operations of a capacitor? So to look at that, let me introduce the notion of capacitance first. So what is capacitance? Capacitance is the unit that tells us how many charge can a capacitor store, right? So capacitance is measured in farad, and it measures, what does it measure? It measures the quantity of charge that can be stored over the voltage that's applied to across the terminal of your capacitor. So for example, imagine if we apply a certain value of voltage across the capacitor, there will be a certain amount of charge that can be stored in that capacitor. So basically, capacitor acts like a battery that can store charges, but the stored charges divided by the voltage is what we call a capacitance. So the value of capacitance depends on multiple things. For example, it can depends on the geometry of the capacitor. It can depends on the material of your plates and your dielectric. It can depends, of course, on various geometrical parameters such as the distance between the plates, the size of the plates, and so on and so forth. Right. So now we're going to look at the basic principle of operations of a capacitor. Okay, so let's imagine we have a capacitor. So we know that a capacitor is basically two plates, right? So we'll draw two plates of two plates that conduct electricity, right? Conductive plates. And then in the middle we have dielectric. So dielectric, as I mentioned earlier, it is a component that doesn't conduct electricity. So let's imagine now we have a capacitor. So this is a capacitor, but it's not connected to any battery yet, any voltage supply yet. So what do we have in both sides? It's basically there are just plates that are in natural state, are neutral. What does it mean to be neutral? To be neutral means you have an equivalent amount of positively charged and negative charge on both sides, right? So both sides are neutral, the same amount of positively and negatively charged charges. And then what's going to be interesting is when we connect it to a voltage supply. So let's imagine now we're connecting it to, let's say, a battery, right? So a battery that has a certain potential difference. Let's say we put here the positive terminal and here the negative terminal. And as you by now know, positive terminals mean you have a surplus of energy. Negative terminals means you have a deficiency or less energy. So what happens when we are connected with a power supply? We have a terminal where there's more energy and less energy here, and it's connected to a neutral terminals on both the capacitors plates. So what will happen? Let's look at this. It's at this part first, where we have a positive terminal. So here we have a neutral plate. Here we have a positive terminal. Positive terminals mean we have more energy here, right? There's plenty more energy here compared to the neutral plate. If you have more energy here than the neutral plate, what will happen? The thing that will happen is that all the electrons will circulate from the point of high energy to the point of lower energy. So here, when we compare these 2 points, here we have now what we call, if we look only into at these 2 point, here we have a negative terminal, here we have a positive terminal. When you have positive terminal and negative terminal like this, what will happen is the current will flow from the positive to the negative. So what will happen when all the currents flows from this positive terminal to these plates? What will happen is that all the electrons from the positive terminal will be accumulated in this plates. So now it becomes a very negatively charged plate. And now let's look at this part. At this part we have a negative terminal, so it means a very low point of energy. Here we have a neutral terminal. When you compare neutral to a negative terminal, we have more energy in the neutral compared to the minus terminal. So what will happen when we have more energy here than here? The current will flow from the positive terminal towards the power supply, negative terminal of the power supply. And when it circulates in this direction, what happens is all the negatively charged, or all the electron will circulate, goes back to the negative terminal of the power supply. So we are left with only positively charged charges on this part of the plate. So if we look at the end globally, we will have lot of negative charges on this part and a lot of positive charges on this part. So now it becomes polarized and it becomes charged. So the capacitor is now what we call charged, right? So now the capacitor is charged. The next thing that is interesting to look at is what will happen if we connect it to a load. Now we're connecting it to a power supply. Now it is completely charged. When it's completely charged, what we can do is we can take off the power supply and replace it with a load. So imagine we have these plates now, which has a negative terminal and positive terminal charge now connected to a load. Imagine we have a resistor as a load. What will happen is that it will react like a new power supply, just like a battery, and the charges will now flows back into the load and consumed by the load. So now here we have more electrons, more energy. So the terminal is basically a positive terminal. So now it becomes a positive terminal. Here is negative terminals. So the current will flow back in the opposite direction of what we had just now. So all the electrons here, the excess of electrons will flow back into the right plates until both of them are balanced and again becomes neutral. So this is what we call a charging state of a capacitor, and this is the discharging state of the capacitor. So just by having two conductive plates and a dielectric material that avoid the charges to jump from one plate to another plate, we create a small battery which is called a capacitor. So in the next part, now we have seen the basic principle, the construction of a capacitor and the basic principle of its operation. Now we're going to look at a few equations that let us find the electrical parameters, usual electrical parameters in a circuit where we have a capacitor. So the first one is let's take a look at the current across the capacitor, right? So a current, imagine we have a capacitor and a current that goes across capacitor is identified as IT, and the voltage across the capacitor is identified as VT, right? Or UT. So a current across the capacitor can be identified by current can be identified as in general as the quantity of charges that circulates over time. So I equals to dq over dt. right? And in previous slides, we also know that the quantity of charges Q equals to CV, or C equals to Q over V, which means the value of capacitance of a capacitor equals to the quantity of charges that can be stored divided by the voltage applied across the capacitor. So we can say that dq can be replaced by dCV. So now we have current I equals to C dV over dt. So let's take a look at this equation for a moment and understand what does it mean. It means that, you see, we have a current which is proportional to the value of the capacitance of the capacitor, and it is also proportional to the variation of voltage across the capacitor. So what does this mean? It means that if we have a higher variation of voltage, it means if we have more difference of voltages between this terminal and this terminal, then we have a huge current that's flowing, right? That means when we are at the beginning of connection of this neutral capacitor with a power supply, right? Imagine if you connect it with a power supply, it's neutral, connected to a power supply. Now we have at this terminal a very high energy, at this terminal a very low energy. So the difference dV is very high, so we have a very high current. But what happens when dV over dt becomes 0? dV over dt becomes 0, it means the voltage across the capacitor is now equal to the voltage across the the voltage of the power supply. So if it is equal, then dV over dt is 0, so you will have no current circulating. So once it is completely charged, then the current will stop to circulate. So that explains this equation of current, right? So I equal to C dV over dt. The next equation that we can look at is the voltage across capacitor. So the voltage across a capacitor, if we know the value of current which is C dV over dt, and we know that the charge Q is I multiplied by T, but now it's not just I multiplied by T. If you remember, I, the current, is dQ over dt. It's not Q over T, but it's the variation of charges over the variation of time. So we know that Q is the integration of IT dt, and plus QT0, of course, is the charges at initial condition of the charges at time 0, right? And if you know now two things that we know, I equal to C dV over dt, and Q equals to the integral of IT dt. So then, knowing that also Q is equals to CV, we can therefore write the voltage across the capacitor equals to, so it's a constant 1 over C, the integrals of IT dt, and of course plus VT0, the initial condition of the voltage at times 0, right? So that is for voltages. So two equations now that we know. The first one is the current, the second one is the voltage. So knowing the current and the voltage, we can deduce the next electrical parameters, which is the power delivered. So power, we know that power is equals to V, can be simplified as V multiplied by I, and as we know that I equals to C dV over dt, we can therefore calculate the power delivered by a discharging capacitor equals to V multiplied by C dV over dt. And then there's another thing, it's not just power, we can also calculate the energy stored by the capacitor. So energy, when we compare to power, is just the integral of the power, right? The integral of power pt dt. So what we need to do is just integrate the equation of power, so it becomes the integral of CV dV over dt dt. So C is a constant, so we can take out C when we integrate it. So the integral of so we can cancel the dt. The integral of V dV is V square over 2. That leads us to the final equation of energy stored equals to half CV square T, or half CV square simply.